Hi, this is Mrs. Lemke here with you. Today we are doing the recap video. See, I put a cap there. Recap video over Unit 6 and 7 as defined by the College Board numbering, which for us was roughly all of Chapter 4, most of Chapter 6, at least the parts of Chapter 6 that we did, and a little dabble into Chapter 8. Where we did improper integrals, and also some of the other integration techniques, I guess, were technically in Chapter 8, technically. All right, so hopefully this will bring about a lot of good math memories for you. For example, here's a math memory. Here are some posters that are on the wall in my classroom, given to me by a couple students in recent past. The curtains have been there for ages, but these poster folks you might know, there used to be some more beat up posters underneath there. But fundamental theorem of calculus, by nature of being the fundamental theorem, is something that is often tested and might feel to you like they are very different in nature, but actually not. This is the theorem that says basically that derivatives and antiderivatives have an opposite relationship. I still think this is one of the greatest things in humanity, right? That moment for the mathematicians who sorted this out really must have been a stunning thing, because why on earth? Why would the issue have been of slope, of rate of change, be mathematically the inverse of finding area of weird shapes? Like that just, wow, it's amazing. It's an amazing thing. All right, so we do certainly need to know fundamental theorem. We are going to do some at least one problem today that makes use of fundamental theorem. And remember that that whole adventure into the integral side of calculus started out with the idea of a Riemann sum. And so I remember that when we were in this unit, I don't know if this happened to you, Covey's kids, but to my students, it must be my poor teaching, but some of them got a little hung up on trying to write a certain format, right? And saying, okay, I need to have a delta x, I need to have my function, I need to have change in x, it needs to look exactly like this. And yes, true, but what we really want to focus on is the idea that it's rectangles, okay? The idea of Riemann sums comes down to I'm taking a space, I am estimating that space using rectangles. The more rectangles I use, and the skinnier those rectangles are, the better my estimate becomes. And so that's where eventually they say, aha, well, if more rectangles and skinnier rectangles are better, let's make them infinitesimally thin, and let's make it so we have infinitely many. And that leads us, boom, to the definition of an integral, and it turns out to be the same thing that you get when you anti-differentiate. So that's very exciting, right? The idea of going backwards then becomes linked to the idea of area, and like, who would have thought it? That's just a stunning thing. Then another idea that we discussed around this time of the year, this kind of November, December-ish time, is the idea of the integral as an accumulation function. So if I have something that is a rate itself, and then I am integrating it, I am finding how much of that thing I have from time equals A to time equals B. I use time as a for instance. It wouldn't necessarily have to be time, but as the independent variable changes, easiest to think about is time, okay? So the idea that if I'm integrating a rate, I get an amount, okay? And I have bounds on those. That's the change in the amount over that interval. We certainly talked about U substitution a lot. And so we would write down, you know, in our cloud, our substitution cloud, this is what U is. Du is something you have to figure out, you have to account for. There are two different kinds of constants in a U substitution question. So actually that wouldn't be U substitution. So if it was like that, right, I would say, oh, this 5 is just a pain. Okay, so that's just factoring out, right? That's just pulling out a common factor, that every rectangle there would have a multiplier of 5. I can factor out the 5. And I said rectangle because I was thinking about the fact that this comes from Riemann sums. Okay, so if I have a multiplier that I don't like, I can factor it out. And then if I need, because my u is 2x and my du is 2dx, if I need to insert a 2, I balance it with a 1/2. So initially people get a little mixed up about this. There's one kind of movement of a constant that is the constant was in the problem and I wish it weren't. That's just a pull out through the integration sign. And then there's a second kind of having a constant, which is like, oh, I really wish I had a constant. Well, let me put that into the question, but I need to balance it. So I'm actually just inserting a 1. 1 is legal. Okay. We did some other integration techniques. We talked about, things like monom-denom, right? Just having a monomial in the denominator and splitting everything up. We talked about doing like long division. We talked about partial fractions. I feel like I'm forgetting something else. Yeah, I didn't I didn't write notes for myself like I usually do. So I'm like, oh yeah, I think I have this in my head. I might be missing something right there. I'm sorry, you guys. Okay, I'm going to go on to my fun story. We'll see if it comes to my brain as we're talking. Okay, so the first problem that we're going to look at today actually was inspired by a real event that happened at the AP reading. And like, this is the kind of stuff that I just really love knowing about. So one of my online friends was talking about this online a few weeks ago and mentioned something about the banana problem and that the banana problem was inspired by a real event. I was like, oh my gosh, tell me more. And so this is what she wrote, that they were at the reading and they went on break. And it's really interesting. At the reading, you're kind of like treated like you're punching in and punching out. Like you punch in, it's 8 in the morning, you start going. And then they dismiss different groups to go have a 15-minute like restroom and get a snack break. Okay, and then you come back at the end of those 15 minutes, you better be on time. And you keep reading until lunch and then the same, and then afternoon break the same. But it's those, yeah, but otherwise, like, you're working. Anyway, so they went on their formatted break, both in the morning and in the afternoon, and they ran out of bananas at the snack table. And so the readers said they were really disappointed. They wanted the bananas, and they said so. Not sure who heard, but after that, there was a full table of bananas every day, piled high. Depending on when your break was, the pile obviously diminished, but we never ran out again. Well, you see, the people at the reading, not all of the people at the reading are people who write the test, obviously, but the test writers are certainly there at the reading. And they just found this amazing and thought we should have a banana-themed problem. And a couple years later, they did, because it does take a while to get through test development. But that year, I was a little sad because this was actually an AB only question. I was teaching BC already at this point, and I was a little like, oh, I want to know about the banana question, because these banana memes, they're great. I mean, honestly, you guys think I like math is why I teach calculus? No, it's so I can understand the memes in May. I hope we get memes somehow this year. I don't really know what's going to happen. Anyway, so the 2017 exam is the one that had the banana problem. So probably that story happened in like 2015. That would be my guess. All right. So when a certain grocery store opens, it has 50 pounds of bananas on a display table. Customers remove bananas from the display table at a rate modeled by blah, blah, blah. Okay, this was a calculator active question. Even without my knowing that to tell you, I hope that when you look at that, you say, oh yeah, this must be a calculator active question, because that's a disgusting function. Okay, so customers are removing bananas from the table at a rate. Notice I already circled the word rate. That is because they did not use a prime here. They aren't not signaling me with notation to think of that as a derivative, but the word rate means in my head, I need to think, oh, that's like a derivative. Okay, and so F of T is measured in pounds per hour. That's good to know. T is the number of hours since the store opened. After the store has been open for 3 hours, store employees add bananas to the display table, again, at a rate. Okay, now this is like the rate of banana removal, this one up here, and this is the rate of banana adding. Oh my gosh, this is horrible writing. I'm getting so lazy, like sitting on the couch all the time, as I'm not actually sitting at a proper desk like ever. Between the sweatpants and the couch, my handwriting is getting worse. I think these are both factors. Okay, so there's banana removal and there's banana addition. I refer to this as a flow in, flow out, and that is because one of the first times I saw this question was on also an old AP test. I want to say maybe like 2014. there was a pipe that was like having water go into something, and then there was water going out of something. There was a question actually last year's test about fish. I feel like that question also was like fish being added and then fish swimming out of a pond or something like that. It's a common theme, okay? So if you can just look at this and be like, oh, this is just flow in, flow out, a lot of them were kind of the same, even if they aren't about bananas. Okay, so part A, okay, this is just the stem printed again. Here's part A. How many pounds of bananas are removed from the display table during the first 2 hours the store is opened? So notice the units actually help you. Sometimes people don't like story problems, but sometimes the story is useful. Your answer here is supposed to be in pounds. And notice that the function was in pounds per hour. How do you remove a rate? You are right, you anti-differentiate. And I'm not going to write that function. Are you actually kidding me? No way. Call it F. They called it F. They named it. Use the name. Okay, so we're going to integrate F from 0 to 2 on our calculators because gross, and we're going to find out a number. Okay, so give me 1 second. Okay, I didn't want to give away the surprise, but here is part A's scoring rubric. If you plug that on your calculator, you get that number. You remember to round to 3 decimal places. And you say that it's that many pounds of bananas that are removed from the display table during the first 2 hours. On the scoring rubric, you get a point for having the integral. I would imagine that would require the bounds as well. So this is a point, and this, the answer would have to be with interpretation, talking about pounds and what you're talking about. All right, for this part B, it says find f prime of 7. Honestly, this is telling you what to do. So like this is not that hard. You're just going to use your calculator. Do not write this on your test. Okay, that is what you're doing on your calculator, but that's not math talk, that's calculator talk. We don't have calculator talk on our test. All right, so you're going to say what you get, and I'm going to peek because I don't have my calculator in front of me. Yes, negative 1.820. Is that what I actually read? 8120. I thought I inverted that. Okay. Sorry. Okay, so you get this number, and now you have to explain it. Okay, now that's a little bit more. But understand that this was also a rate. This is a flow in, flow out, yes? So this was customers removing bananas at a rate. So this is bananas per hour as well. So if I'm differentiating this, this is saying the rate at which the bananas are removed when time equals 7 is that rate, that many bananas per hour per hour. The rate of a rate. All right, part C. I want you to try part C on your own. Okay, so part C is the number of pounds of bananas on the display table increasing or decreasing at time equals 5. Give a reason. And how many pounds of bananas are on the display table at time equals 8? So those are parts C and D. I'm going to go back to this slide where all of it's visible. And I'm going to ask that you hit pause and try C and D. Okay, so if I want to know if the amount is the amount of something is increasing or decreasing, I want to know if its rate of change is positive or negative. And the rate of change in the bananas is the rate at which they're being added minus the rate at which they're being subtracted. In other words, f of t minus g of t. And I want that when time equals 5. So here we are on the banana colored slide. What, did I just say that backwards? I did. I'm so sorry. This is the rate at which they're being added. This is the rate at which they're being subtracted. Heavens. Okay, so g of 5 minus f of 5, okay? And since that turns out to be negative, that means the number of pounds of bananas on the display table is decreasing of a negative rate of change. Okay, and then part D, how many pounds of bananas are on the display table at time equals 8? It's important that you get this. I don't know if they're going to be so devious this year, But sometimes there is some little factoid in the stem of the question that you don't use until part D. I think it's kind of mean, but they also kind of do it a lot. So, I mean, like, bad on you if you don't realize that. Okay, so how many pounds of bananas are on the display table at time equals 8? Okay, so now that I got this straightened out in my head, that F is the one that's like the people taking the bananas from the time that they open until time equals 8. This is the amount of bananas that would leave. And then the people putting the bananas back on don't start until the 3rd hour. But then they are putting the bananas on at that rate. So we're going to work that out. We're going to utilize our calculator features, and ta-da. Okay. All right, you can check the scoring rubric for points. But that is a classic flow in, flow out question. All right, one other thing that I'm going to talk about before saying bye is improper integrals. So there are 2 kinds. I don't actually know if this is a word. I think it's a word. Impropriety, that's a word, right? I don't know if I'm using it properly, or maybe I'm using it improperly, which would be kind of ironic. Anyway, improper integrals. There's 2 different ways in which an integral can be improper. One is really obvious. You'd have like a bound here and then an infinity and then something. Or you'd have like negative infinity to positive infinity and then your integrand. Like that is like smack you in the face with the impropriety because hello, infinity, right? And so you have to rewrite that as a limit with an infinity sign, right? Or and this one you have to rewrite twice, right? You have to kind of split it up. You pick someplace in the middle, like 3, and go negative infinity to 3, and then 3 to infinity, and then rewrite both of those things I just said with a limit. Okay, but still, you're not going to miss that. The subtle one is the one that, oh man, it can just get you. That guy. What's wrong with that guy? Looks like something I could just integrate. False. There's a vertical asymptote at 4, which means your function is not continuous from 3 to 5. Those bounds of integration, they jump right over a discontinuity. So you got to split that guy up. You got to split it from 3 to 4 and then 4 to 5 and then rewrite both of those as a limit going towards 4, coming from one side or the other, always come from the inside, right? So I'm not really explaining this because we did explain, you already know this, but I just want to remind you, okay? So there's 2 types. There's the obvious type and there's the less obvious type. Both of those require rewriting as a limit, okay? So here is another question. A theme of today is 2017, by the way. So the banana question was 2017. This was a 2017 question, but this was on the BC side only, not the AB side. And you can see that all this question is great, but the part I wanted to look at today was the part that I have put a red box around. So it says, using the identity that blah, 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 blah. Now, first of all, this is being like so ridiculously nice because did they have to tell you the partial fraction decomposition? No, they could have made you find that. So, woo, getting soft, College Board. Okay, so using this identity, evaluate this integral. Okay, so I'd like you to pause and then come back after you've done part C. Okay, welcome back. So the first thing I want you to notice is that we are fastidious as mathematicians. I know for a fact that your physics class, even your physics C class, does not make you always write this notation. I think that is sloppy, okay? So infinity is not a number. It should not be treated as such. So make sure that you remember what class you're in. You're in calculus. We should be precise. So we're going to rewrite that infinite bound as a limit. And then if you call the upper bound b, then you say as b goes towards infinity, or whatever letter you put up there, okay? Not an x. Don't use x. X is already taken. All right, so we write that, and then we use the identity that they gave us. And then this is so nice of College Board. Like, I would have made this question be so much worse. You've experienced it all year, okay? So this bottom part has a derivative right here. And same on the other fraction. It's already set, like you didn't even have to tweak it. That's really, really kind of them. So this is going to be a natural log minus a natural log. And then you can use a property of logs. Like there's more than one way to get to this, but the nicest way is to use that property of logs to divide. And then you're going to substitute in your bounds. And then you're going to evaluate the limit. And you know that this quantity, as b goes to infinity, the -5 and the -1, not so important. It's going to act like a 2. So this is like log of 2. As b goes to infinity, it's like log of 2. And then you have that constant there. And you could do this, but honestly, like I wouldn't do that. Okay, I was supposed to be crossing out, not highlighting. I wouldn't do that. I would just stop right here because that's a number. Okay, and that's great. No one's going to count that wrong. That's awesome. Okay, now part D, which you maybe didn't have a chance to read yet, says determine whether this series, now this series is based on this, right? They're just now taking the sum of it. Okay, so if that's, determine if that series converges or diverges. Now, what would be the easiest way of doing that? Think of what you just did. Yeah, use the integral test. Of course, if we're using the integral test, we want to make sure that we check the boxes, right? Say, I get to use integral test because I have a function that's continuous, it's positive, it's decreasing on the interval that we're talking about. And therefore, I have convergence because if the integral converges, which it did, I just did that, I know the series converges also. So of course you could just ignore the fact that you just did part C and talk about, like limit comparison test if you wanted with a nice P series like 1 over n to the second or something, but whatever. I mean, you do you. I think that's where I'm going to leave off. Yes, that is where Mr. Covey's going to pick up from. He's going to start right here on this purple slide, I think. Thanks, you guys. We miss you so much. Teachers talk, and we talk all the time about how much we miss seeing our students and talking to you and seeing your enthusiasm. And it is really sad that we're not in school. It breaks my heart, but I am glad that we're trying to stay safe. My husband's diabetic, and I am thankful for the efforts that every one of you make that help keep people like him from getting sick and landing in the hospital. So thank you very much, and we'll see each other sometime. We really will. Okay, bye.